Hello, my name is Walter Ellsworth, and welcome to my presentation of Lab 5, Magnetic Braking with Faraday's Law. The purpose of this lab was to use Faraday's Law and the known qualities of a time-varying magnetic field to create a computational model and then predict how long it'll take a magnet to move through a tube of aluminum foil. Uh, the results of this entire procedure were that it took about 0.738 seconds on average for the magnet to move through the tube of aluminum, and the computational model predicted a time of 0.601. The models and physics principles that were used in this were Biot-Savart's law, Faraday's law, Newton's second law for the force of gravity, Ohm's law, the change in inductance in relation to time, which we went over in class, and the magnetic force on a wire. The the pipe acted as a series of rings that supply the counteracting force to gravity. Each ring supplies its own uh, portion of force, and in addition, they all supply enough to slow gravity, to slow the speed. A magnet. The details of the experiment. A magnet was dropped north side down a tube of aluminum foil, and the time was recorded by me using my phone to as it took to fully pass through 5 times, and using measured physical values and known formulas to create a computational model, and then that model was also created using Python. And the initial conditions were that the magnet with the North Pole dictated, and the tube of aluminum foil was held vertically. But I used my hand to hold it, so it wasn't secured super well. And the system in the surroundings, the magnet is the system, and the tube is the surroundings. These are the measured times that I got. It was me using the timer on my phone, so not the most accurate method. The aluminum was 0.27 meters, width was 0.0025 meters, inner radius, magnetic dipole, magnet mass. Used a magnet that I got off Amazon. This is the updated code that I went back through and put in the values that were given, or that are in the formulas, and then the values that were taken through the experiment. And this is it continued. This is what the computational model looked like as it was at it after it finished running, and then at the on the right here is the graph of its velocity over time. Possible errors in this lab. The largest error is most likely a personal error using the stopwatch accurately, and some of the other errors could have been friction from the magnet as it was going down the tube, because I wasn't holding it straight too, so it could have hit the sides, and air resistance was completely ignored, so that definitely did something. What if the resistivity of the conductor was reduced to as close to as possible zero, and how would the dynamics of the falling magnet change? Since according to Ohm's law, current is inversely proportional to resistance, the current would increase. This means the braking force would increase to a point where it could equal the force of gravity and stop the magnet from falling out the bottom. But that's almost impossible to get easily. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? If you cut slots into the tube, you're effectively decreasing the amount of rings, which means that there's less current and therefore less force generated against gravity. So the magnet would just fall through a lot faster. Uh, Thank you.